Hello friends, a very good evening to all of you. So today I am starting a new series on data structures and algorithms. And just a brief introduction about myself. I am Arpit Gupta. I am staying in Noida, India, and I'm a software engineer by profession. And I mainly program in Java and a very little in C++ as well. Okay, so let's start with the problem that we are going to discuss. Right, so here is the problem that we are going to discuss. What we have here is a classical knapsack problem. Now this knapsack problem is a very famous problem in computer science, and it is you'll find it in any data structures and algorithms book. And we're going to make sure that we understand the problem, we find the solution to it, and we do it in a manner so that it is easily digestible and does not burden the brain too much. Okay, so what is the problem? The problem is that you have a sack, you have a bag which has the capacity to carry W kgs of weight, right? It has the capacity to carry W kgs of weight, and there are a lot of items which are of different weights. There is 1 kg, 2 kg, 7 kg, 10 kg, 15 kg, and each item has a price associated with it, right? Number of items is n. Each item is characterized by wi, that is the weight, and a value vi, right? So the problem is that you want to maximize the value of the items that you can carry in the sack, but at the same time ensuring that the total weight of those items is less than the capacity of the sack, that is capital W. Alright, so this is the problem. Now you can pause the video and take a moment to think how we are going to solve this problem. Okay, so we are going to discuss a few approaches to solve this problem. The first approach and the most obvious one is the brute force approach. Now what is the brute force approach? The brute force approach is that you simply consider all possible combinations of the items, and you will check whether the combination of the items yields a weight that is less than equal to W, that is this. That is the condition you're going to check. And the second thing that you're going to see is the price. And you're going to store it, you're going to remember it in a variable. Let's call it max. So if this condition is met, then you are going to calculate the total value of those items, and we'll call that thing as val, and we'll also store a maximum, that is max. So if the current value is greater than or equal to max, then the max will be reassigned to this value. So we'll do this for all possible combinations, and finally we'll arrive at our global maximum, right? Now the only problem in this approach is that we need to calculate all possible combinations. Now how do you calculate all the possible combinations? Well, it's simple. For each item you have the choice. For item 1, 2, 3, 4, you have choice. The choice is whether you want to select that item or you want to not select that item. So it's a 0 or a 1. That is why in fact it is called a 0 by 1 knapsack problem. So if you select that item, it's a 0. If you don't select, if you select that item, it's a 1. If you don't select that item, it's a 0. So for n items, what is the combination? What is the total number of combinations? It's going to be 2 into 2 into 2 n times, which is basically 2 to the power n, right? Simple enough. So for n items, the total number of ways in which you can select the items is 2 to the power n. We can go back to our maths class, which we learned in our school days, probably in the 11th and 12th class, and recollect what is the total number of combinations which are possible to select the items, to select a subset of the items, right? Now, what is the problem with this approach? You see, if n is small, if let's say n is less than equal to 10, this approach works fine. But as soon as n becomes large, then the problem of finding the total number of combinations itself is a huge task. So I just calculated a very basic rough idea how the 2 to the power n grows as n grows. So you see that for 4 and 10 it's okay, but as soon as it comes like this, n is equal to 30, the number of possible combinations to select the items grows to a very huge number. It is 2 to the power 30. It's approximately 1 billion. And that is why this approach does not work for large values of n. And therefore, we generally do not go by this approach, this brute force approach. Right? Okay. So then what is the approach that we're going to follow? We are going to follow the dynamic programming approach. Now, if you have studied computer science, then you know that what is a dynamic programming approach. Dynamic programming basically means that you solve the problem recursively, you break down the problem into smaller subproblems, you solve the problem recursively, and then you store the result of each subproblem in an array or a matrix or any data structure that suits your purpose. But the idea is to store the result of each computation at some place in the computer memory, so that you do not have to recompute that same subproblem again. And that is how the complexity of the problem, the time complexity of the problem is reduced, because you're not calculating the result of that computation again and again. So that is the dynamic programming approach. And let us see now how we can apply the dynamic programming approach in this case. So what we have done here is, we have taken a small example to actually illustrate how we are going to solve it using dynamic programming. Here, the total weight of the sack is 10 kg. Number of items is just 4 for sake of simplicity. You have 4 items, 1 kg, 3 kg, 6 kg and 8 kg. Here is our Wi, and the price or the value of those items is correspondingly 1, 4, 8 and $12. You can see the array Vi here. Right? Now we have written a function called max value of knapsack. This is a recursive function. Let's try to understand what is the meaning of this function. What do we want this function to do? So maxval I comma j represents the maximum value that can be achieved when the remaining capacity is I. Because as we fill the sack with items, the remaining capacity of the sack to carry weight is going to get reduced. So initially this I is going to be 10 in this case. Initially it's going to be 10. And what is this j? J is basically are items in serial order which we can choose from. So for j equal to 1, basically means you can select items from 1 to 4. J equal to 2 means you can select items from 2 to 4. So j equal to 2 basically means that you have already taken the decision whether or not to select item number 1. You don't need to consider that in that particular subproblem. So initially our problem is to find this function maxval knapsack. Initial weight is 10, initial capacity is 10, and you are allowed to choose all the items. that is from 1 to 4. So we have drawn a matrix here, a 2D array. The columns are the items and the rows are the weight, is the remaining weight, remaining capacity of the sack, right? So we are here right now in the beginning, in this place. This is where we are. So we want to calculate what is the maximum value of the items that a sack can carry, provided the remaining capacity is 10, and you have a choice to choose from 1 to 4 items. That is, you have all the items to consider right now. Now we are going to break down this problem into sub-problems. Okay. So let us see how we can break down this problem into sub-problem. Now if you see, what is the capacity, what is going to be the function that we're going to call if we select the first item? You see the first item here, this is the array. Consider this again. If you select the first item, then you have, initially the value was 0. So what you have done is you have increased the value of the sack by 1 value. And what is the weight? It is 1. So now the remaining capacity of the sack is 10 minus 1, that is 9. Right, 9. So this is the function that we can call. So the choice is choice 1, select item number 1. What is the choice 2? Do not select item number 1. So if you take by the second choice, the remaining capacity remains the same because you have not selected that item, that is 10 here. And the choice is, again, you can select items from 2 to 4. So here we are. So in the first choice, we are at this position in the matrix. For the second choice, we are at this position in the matrix, that is 10, 2. Now, so what is the now, so we are here, right? So what we want to find is which is maximum, which value comes maximum in choice number 1 or in choice number 2. So we take a max of this. That's why we return maximum. So whether this is going to be large or this is going to be large, we do not know in advance unless we actually calculate the value at this place, and at this place we are not going to know which is maximum, right? And this process continues recursively, it goes up and down. So suppose we are at this point now, maximum value 9, 2. Let's do one more iteration and we'll see how it goes. Is this thing right? So now we are at this position. What position? We are at 9, 2. Okay, we are at this position in our matrix, right? So max of knapsack 9, 2 is equal to max of 4. For choice 1, select item 1, select item 2. You have selected item 2, its price is 4, as you can see. 4 plus max val knapsack. Now its weight is 3, right? Now we were at 9. The remaining capacity was 9. 9 minus 3 is 6. The remaining capacity remains 6. So the first choice, that is this. If we select item number 2, we need to compute max val knapsack 6, 3. And if we do not select item number 2, we need to make calculation of this 0 because we have not selected item number 2, and again we recursively call this function 9, the remaining capacity remains the same, and 3 basically means again this position in the matrix, which means that you have a choice to select items number 3 and 4. Okay, again I am going to repeat this thing, that any position in this matrix, let's say this position, this is 4, 3. Now one thing to remember is, right now for the sake of simplicity we are using 1 based indexing, but when we actually program the solution it is going to be a 0 based indexing solution, because generally in C++ as well in Java we have a 0 based indexing, but right now for the sake of understanding the things we are using the indexes as 1, 2, 3, 4 and 1 to 10, right? Now, so what does the index 4, 3 mean? 4, 3 means that the remaining capacity of the sack is 4 kgs, and you have a choice to select from items number 3 to n. Okay, right. So now we are going to try to generalize the function of this function Maxwell knapsack. Now here I have written knapsack just for the sake of shortcut, but actually this knapsack is again Maxwell knapsack. That is the maximum value that the knapsack can carry, the first argument being the remaining capacity of the sack, and the second argument being j, which means that you have j to n items to consider. Okay, so the solution of the original problem is to find the maximum value of the knapsack 10, 1. 10 is the remaining capacity of the sack, is the original capacity of the sack, and 1, which means that you have all the items to consider from 1 to 4. Here is generalization of the recursive function. At any point in the matrix I, j, we need to calculate the maximum of Vj. This is the select case when you are selecting the jth item. This is the select case, and this is the reject case when you are not selecting the item. Right, and of course you have to take care of the terminal cases. So terminal cases basically means, if you go back to the main, if our matrix, suppose you are here in the matrix. Now if you are here in the matrix, you have basically reached a stage where you cannot go up. You cannot say because the remaining capacity will be 0 after this, and also it may happen that the weight of this item, that is item number 3, may actually be larger than the remaining capacity, in which case you simply cannot take that item. So you have to go here, and if you are here, then again you have just this particular item to consider. If the weight of this item number 4 is greater than the remaining capacity, that is 1, then you simply return 0, because you just have to waste away you cannot do anything with the remaining capacity. So these are the terminal cases that are mentioned, and we have to take care when we are programming the solution. Okay, now we come to the part of programming. We are going to consider two approaches to solve the same problem. In dynamic programming, generally there are two approaches that are very popular. One is memoization and the other is tabulation. We'll see the approaches one by one. Now approach number 1 is memoization. Memoization basically means you are remembering, you are proceeding recursively, and you are storing the result of a of a of a problem which is lower down the order. Okay, let us go again. So the approach number one is memoization. Memoization is nothing but a recursive solution. The only difference is that you store the result of each recursion step in a 2D array. Here our array is of size w into n, right? So here I've created a kind of visualization to help you understand what happens. Red means you are selecting that item, green means you are rejecting that item. So at each step in our matrix, we have two choices: whether to go up like this and little bit to the right, or which means you are selecting that item. Second choice is to go like this. You don't select that item at each step in the matrix. So this solution is a very good one, and I personally prefer to follow this approach, memoization, because it is more intuitive, and the way you formulate the problem, this thing, it generally it gels well with this approach, memoization. It generally is very easy to understand and solve this problem using memoization first. And the only problem with memoization is that if your n and w are large, then your recursion stack actually becomes very large. Your recursion stack becomes very large, and it occupies a lot of space, and sometimes it becomes so large that it may cause out of memory error also, because the recursion stack grows exponentially. So suppose you are here in your stack and you reach somehow this place. To reach this place, you might have to go through maybe something like, it again is an exponential problem, so it grows like this, 2 to r n. So the recursion stack becomes very huge, and then the problem becomes intractable. Now to solve this problem of recursion stack, there is another approach that is called tabulation. This tabulation approach is called the bottom-up approach. If you read any book in computer science about dynamic programming, they will call it as the tabulation or bottom-up. Why is it called bottom-up? Bottom-up basically means before calculating the larger problem, we make sure that all the sub-problems that it dependent on, they're already calculated. So for example, in this particular case, we have taken n equal to 7 and w equal to 35. So we are here in the matrix. In order to solve this problem, we might have to jump to this place and this place. But what if this step and this step, they are both already calculated? So we see that in this approach we are going right and we are going up. So what if we start from here? If we start from this place in our matrix, if we can solve this problem, and we go like this, we go from 0, we go from 0,6, right, till 0,0. So we are going like this. We are solving each problem like this, okay, from right to left. And then we go down, then we go 1,6, like this, like this, like this. So if you follow this approach, then there is no recursion required, because the subproblem that you want to calculate later, so its subproblems are already calculated. Please try to understand these things. Suppose you are here. Suppose you want to calculate this step. Let's say this is 4, 2. You want to calculate the solution to this subproblem, and let's say its weight is 2 kg. The item number 2 weight is 2 kg, right? So it will want to calculate, it will go till here, it will jump till here, right, at this place. But this is already calculated. If you select it, then you want to calculate this subproblem. If you do not select it, then you want to calculate this subproblem. In both cases, because you're going right to left and you're going from top to down, these two subproblems are already calculated. So in this case, you do not need to calculate the subproblem again. They're already there for you. So there is no recursion required. You just calculate the value of all the subproblems, W into N. That's it. No recursion required. There is no recursion stack. And you get a solution very easily, very conveniently, right? So what is the time complexity? Using the dynamic programming approach, for both tabulation as well as memoization, the time complexity is O W, that is the capacity of the sack, into N, that is the number of items. Space complexity is again O W into N, because we have a 2D array which is of this size. In case of memoization, this time complexity and the space complexity is a little more because of the overhead of recursion. So the space complexity is generally a little large, and the time complexity also can be a little bit more, because when you call one recursive function again and again, it takes some time as well as some space. But generally, if W and N are not too large, then it won't matter. But if the W and N are large, then you may face some problem using the memoization approach. Okay. Now let us see something in context. Suppose our N is equal to 30 and our W equal to 100, right? What is the complexity using brute force approach? For brute force approach, the only item to consider while calculating the complexity is N. So the complexity is O 2 to the power 30, which is roughly 1 billion. For the dynamic programming approach, you have the complexity as O N into W, which is equal to O 30 into 100. It's roughly 3000. See the difference? Here it is 3000, here it is 1 billion. You can see the difference. And that is why dynamic programming is considered such a powerful technique in computer science. Right. So we have come to the end of our lecture. I will be uploading the solution to this problem in Java, and we will find it in the description of the YouTube video, right? So it will be a GitHub link, and you can go through the solution in Java using the dynamic programming approach using that link, right? All right, we are all done here. Thank you very much for watching, and please do write what you feel in the comments so that I can also improve myself and I know whether you have actually liked the video or not. Okay, bye bye.